All right, so today we'll finish up section 11.2, okay, which is on a series. Only difference between the kind of series we looked at yesterday and today is yesterday the series were all finite. If a series is finite, you can always find the sum of it, always. But if it's infinite, well, whether or not you can find the sum, that depends. And we'll look at some different examples and see if you can just look at a problem and determine, would this add up to something if you added up infinitely many terms, or would it not? And then if it would, you have to figure out, well, what does it add up to? Okay, so there are some types of series that you can add up infinitely many terms and you get an answer. It adds up to like a number. But then sometimes it doesn't. Okay, let's think about an arithmetic sequence. What's the rule for an arithmetic sequence? How do you get from one term to the next? You're adding or subtracting, yes. So if you had an arithmetic sequence, all right, like let's say 3, and we just add 2. And I'm going to put a dot, dot, dot because it goes on forever. If you add up all the numbers in that sequence, would they add up to a number? No. How come?
Because they're constantly growing.
Yeah, they're growing, all right? And with an arithmetic sequence, it's always growing. It doesn't matter if it's growing bigger and bigger and bigger towards like positive numbers or towards negative numbers. Arithmetic sequences, the individual terms always approach infinity or negative infinity. Okay? Even if you add a really, really small number, like let's say you only add 0.01 each time. Well, if you go to infinity, it's still going to grow forever. So arithmetic sequences, if you try to add them up for infinitely many terms, they don't add up to anything. So that leaves us with geometric. And those are the ones we're going to pretty much focus on. All right, so that's the notation to add up infinitely many terms. Okay, I have sigma notation on the left, expanded notation on the right. What's different in the sigma notation today? Yeah, you have the infinity symbol on top. And what's different on the right-hand side? How could you tell just by looking at the right-hand side that this is different than yesterday? No? Yeah, it doesn't end with the nth term. It goes beyond it. Okay? And there's a dot, 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 which means it goes on forever. Okay? So that's the notation that you would see either sigma or expanded for an infinite series. Okay? And I already mentioned the idea that if you're going to add up infinitely many numbers, you obviously can't do that directly. Even if you had to add up 1 billion terms, you can do that directly, or a computer could do it. Okay. But infinitely many terms, no. We've got to figure out a different way to add them up. All right, and the way we're going to look at it first, we're going to think of it visually. Does anybody remember when we had certain types of graphs, and as they went towards infinity, they would get closer and closer to a value. They would never reach the value, but they would get very, very close to it. And sometimes we would put a line, or a dotted line, at the value that it gets very, very close to. Does anybody remember what that dotted line was called? Yeah, an asymptote. So that's pretty much how we're going to think of adding something up to infinity. We're going to look at a graph, and we're going to see, is it getting closer and closer and closer to a value, but never reaching it? If it is, then that value that it's approaching is what it would add up to, okay, if you went out towards infinity. So we're going to think of it as it's going to be getting closer and closer and closer to a value. All right, so the idea is that if you have a number, and call it s, and you graph the horizontal line y equals s. Okay, so if s was 3, you graph a horizontal line at 3. If that line is a horizontal asymptote for the sequence, S sub n, okay, so this means you need to figure out the formula for the sequence. So you have something to look at. Okay, but if that line is a horizontal asymptote for the sequence S sub n, then what we say is S sub n is converging. Okay, converging means that it's adding up to something. If it's not adding up to something, we say it's diverging. Okay, so we say that S sub n is converging to the number S. And again, S is where that horizontal asymptote would be. It's what it's getting closer and closer and closer to, but it's never actually reaching it. As you approach infinity. And S, that where we have the horizontal asymptote, that is the actual sum, right? whatever the asymptote would be. So kind of the really short way to say that, if you just want to use a notation, is that as n approaches infinity, the nth partial sum approaches S. Again, what's S? It's the number that is a horizontal asymptote for the formula for that. Now, the difference when we graphed equations before that approached asymptotes is they looked something like this. We talked a little bit about this either yesterday or probably the day before. When you graph a sequence, does it look like that? What's different when you graph a sequence? Well, it could still curve. I mean, we don't know exactly how it's going to look, but there's something fundamentally different about the graph. Yeah? It's not continuous. So if we had a horizontal asymptote like that, and we graph S sub n, okay, the sequence of partial sums, it might look something like this. You're going to get individual numbers, like the first term, second, third, fourth, fifth, sixth. It's getting closer and closer. So on the calculator, we can't graph individual numbers like this. The calculator is going to graph it as a solid line. But you have to think in your head, all right, really, I'm just going to focus on integer values for the domain. Okay? There's nothing between 1 and 2. Okay, 1.5, plugging that in doesn't even make sense in this case, because we're thinking of positions, okay, in a sequence. So to think about an infinite series, we're not really looking at a sum. What we're looking at is a sequence of partial sums really, 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 really far away. All right? That's the best we can do. Right? Because it's not possible to add up infinitely many terms. So what we might look at is, what would happen if you add up the first 10 terms? Right? Then let's go a little further. What happens if you add up the first 100? What happens if you add up the first 1,000? Right? We're just going to look way, way out and see what does it look like the pattern is if you add up a really, really large amount of terms. Okay, so we'll look at the number that's really, really far down in the sequence of partial sums. And usually, I say you have to go way out. You usually don't even have to go that far. Usually, these kind of graphs converge very quickly. So if you add up like the first 6 or 7 terms, that's usually going to predict what would happen if you added up the first 2,000. Okay, it converges really, really quickly. All right, so that's just I'm writing down what we're doing. We're taking a geometric sequence, that's the formula, and we're finding the sum of it. Okay, so we're basically doing what's on the right-hand side. Okay, so let's try it for this one. Does everyone have what's up above the sigma?
No.
So this one is asking us to add up from 1 to infinity. And the sequence is 2 times 1/3 to the k minus 1. Well, what I'm going to do first is if I want to graph something, I have to pretend almost like this is a fixed value. Right? I'm going to try to think of this using the formula we had yesterday. And all I'm going to do is look at that formula that we used yesterday, but I'm going to let this be a really big number. I'm going to look at it way out and see what's happening. So can somebody remind me again, what's the formula for the nth partial sum of a geometric series? Yep.
Parentheses, minus r to the power of n
Yep.
divided by 1 minus r.
Minus r. And that is the value we're going to look at way out. We're going to let n be a really, really big number. Okay, so I've already done some of these out. Okay. A1 is, the first term is 2. Okay, how do I know that? Well, it's the number that's right there. If you didn't know that, all you have to do is plug in 1 for k, do the calculation out, and you'll get 2. Because if you plug in 1 for k, you get 1/3 to the 0 power, which is 1. And then 1 times 2 is 2. So 2 is the first term. And the common ratio is right there. 1/3 is what I'm multiplying by each time. Okay, so I filled in the formula Quinn just gave me. And I did it for what happens if you add up the first 4 terms. And even just adding up the first 4, I can already see it looks like it's approaching a number. Okay, what does it look like it's getting close to? 3. If you add up the first 5 terms, okay, that confirms what we just said. It's about 2.9877. And then if you add up the first 6 terms, okay, just changing the exponent to a 6, you get 2.9959. And I didn't do these calculations out. The way I did it is I type in the formula, and then I use the table on the graphing calculator. Okay, so let me show you how we can do that. All right, so we type in 2. And then we have 1 minus 1/3, and I have to do to the x. I can't use n as the variable. You have to use x. And now we have to be kind of careful with parentheses. So if I close that, that's my numerator. And then divide by, I'm going to open it for the denominator. And what's 1 minus 1/3? I'm just going to simplify that. 2/3. Close the denominator. And then close that, and hopefully I have the same number of parentheses opening left and opening to the right. Yeah, I think we're good. So let's go to the table, and let's type in 4. Get 2.963. If you let it be a 5, that's the 2.9877, and there's the 6. So now if I want to see, well, what happens if you add up the first 20 terms? It says 3, but remember, it's rounding it off. Okay, so you don't even have to get anywhere close to infinity. Just adding up the first 20, it's already like 2.999999999. If I go much more than 20, it's just going to round this number off to a 3, because I'm running out of decimal places on the screen. Okay, but that's the idea of how you do an infinite sum. Okay, let's try to just visualize it. We think it's at 3, right? So I'm going to put a horizontal line at 3. That's going to be in red. And I don't need to look at negative terms. That doesn't make sense. And this particular sum isn't negative. It could add up to a negative number, but this one doesn't. And I know I don't even have to go as high as 10 because it looks like it's maxing out at 3. So I'm just going to go to 5. Okay, there's my partial sums. Remember, you want to think of that as being dotted. Okay, a dot. So really, we should only be seeing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 right on the edge of the screen, dots. And that red line is an asymptote. Okay, those dots are getting closer and closer and closer to 3, but they're never going to reach it. Okay, it looks like it does because of the resolution of the screen. So any questions on that? Why this sum is approaching 3? Right, so I think if you think about it as an asymptote, it's getting closer and closer and closer to a value. That kind of makes sense. But there's a way we can do it without having to do this like guessing stuff, like typing it in and then trying different numbers to see what's it getting close to. Right, there's a formula we can use, and it's a lot faster than this. All right, so we already visualized it. And this is how you visualize it. Okay. To draw a picture of the sums that we just had, okay, I specifically did S4, S5, and S6. But to draw the whole picture, you type in this formula. It's a little tricky with all the parentheses. You gotta kind of be careful. And remember, focus on the positive integer values for x. Right, so what, let's see, let me put this here for a second. All I should really be seeing in this picture is these green dots. I should see one there, one there, one there, one there. All right, so that's, actually there's no 0th term, I'm sorry. So all you should be seeing is those green dots. Okay. Beyond that, they're just gonna blend into the red line, so it's kind of hard for me to draw them. Okay, so pretend like that blue line, that blue curve isn't even there. So focus on positive integer values for x. And as x gets bigger and bigger, that's a good approximation of what your sum is approaching. Okay, and as I said, x doesn't have to get that big. Usually going to like 6 or 7, it's already converging to where the answer is. Okay, what did I say it would be if it doesn't converge? Anybody remember that term? It diverges. And you can say it a couple different ways. You can say here that the partial sums are converging to 3. That's one way to say it. Or you could say the sequence of partial sums is convergent. It's the same thing. All right, so find the sum using a graphical approach. We already did that. That's what I did on that screen. All right, let's try this one. Let's try to find the sum using a graphical approach. Since I already have the last problem typed in, I just have to change a couple things. What is my first term here? 4. And what's r in this case? 3. So it's not 1/3 anymore. It's 3. So we're going to make that a 3. And in the bottom, it would be 1 minus r. So what's 1 minus 3? -2. Okay, technically, I don't need parentheses around the -2 and the positive 3 because they're not fractions anymore, but it won't hurt. Okay, so that's a sub 1 times 1 minus r to the x over 1 minus r. Before I look at the table, any thoughts what's going to happen here? In example 2, what did you multiply by to get from one term to the next? 1/3. So what's happening to the terms as you go further and further out? They're getting smaller. What are they approaching? Not what are they adding up to. What are the individual terms approaching? 0. So there's a difference between what the individual term is approaching and what the sum of the terms is approaching. The sum of the terms is approaching 3, but the individual terms are approaching 0. What's happening here? What are you multiplying by each time to get from one term to the next? Multiplying by 3. So what are the individual terms approaching? Infinity. So the sum here is also going to approach infinity. This isn't going to add up to anything. Let's just look at the table and you can see it. If you add up only the first term, ignore the y2, that's from the last problem. But if you add up only the first term, you get a 4. If you add up the first two terms, well, the second term must be a 12, because the sum of the first two terms is 16. The sum of the first three terms is 52. By looking at this, I can see the sum is growing. It's not approaching a number. Okay, and then if I add up the first 10 terms, now it's up over 100,000. Okay, so if we graph it, that blue line represents the sums. It just goes off the screen very, very, very quickly. All right? And you can see by looking at the table how, just ignore the red line, how quickly. By the time x is 10, y is already up over 100,000. So it's going up really, really fast. So as x heads towards infinity, the graph does not have a horizontal asymptote. It just curves up. Okay? So we say that the series diverges. Okay? Or you could say it's divergent. Okay? Is there any question on the difference between what the terms, if it's converging, what the terms are converging to, or what the sum of the terms is converging to? I just wanted to clarify, because I see that mistake a lot on the test. I'll ask what the series is converging to, what the sum is converging to, and some people write 0. Because that's what the terms are approaching, not the sum of the terms. So just be careful with that. All right, so from example 2 and 3, we can see sometimes a geometric series converges, sometimes it diverges. Okay, I'm going to give you a few examples, and I want to try not to graph them. I just want to look at them and see if you can tell me, yep, that one would converge, or no, that one would diverge. I want to see if we can find a pattern of when things converge and when things diverge. Okay, so in your book, I think it's on page 598, and what they have you do with a graphing calculator is just kind of explore what happens if you let r be different values. Because that's what you multiply by each time, and that's the only thing that determines if it converges or diverges. Any guess what would happen if we let r be 0.8? That would converge. How about 0.9? That would also converge. What would be the difference in the rate of convergence between the two? And so how would the speed at which B is converging compare to the speed at which A is converging? Which one is quicker? Well, think about the individual terms. If you multiply by 0.8 each time or 0.9 each time, which terms are getting smaller faster? Yeah? If you multiply by 0.8, the terms are getting smaller faster. Okay? Take a number like 5, multiply by 0.8 3 times. 1, 2, 3. Okay, you're at 2.56. Now take the same number and multiply by 0.9 3 times. 1, 2, 3. 3.6. So they're both converging to 0, but A is converging faster. Okay, B is converging slower. And if B was like 0.999, it would converge extremely slow. Okay, because each time you're multiplying by something so close to 1, it's getting smaller, but not very quickly. It's going to take a long time for that to converge. How about C? That's going to diverge. And how about D? That's also going to diverge. Which one is going to diverge faster? D is going to diverge faster, because multiplying by 1.2 each time is going to make the number a little, it's going to make it bigger faster than multiplying by 1.1. All right, so what do you think the rule is here? When does a sequence, or when does a geometric sequence converge, and when does it diverge if you add it up?
It converges when r is less than 1, and it diverges when r is greater than 1.
So what if r was like -5? That is less than 1.
Oh, between, yeah, the absolute value of r is greater than 1.
If it's greater than 1, it would diverge. So any number when r is between -1 and 1, it will converge for that. Okay, so that's what this says. If r is anything between -1 and 1, not equal to, because if it's 1, that wouldn't converge. Okay, it's got to be between -1 and 1. And that causes your sequence to converge, the sum of your sequence. So if we want to figure out basically what's happening, what is it converging to? We want to come up with a formula. Let's start with the formula for a finite geometric series. And let's look at what happens when n gets really, really big. Okay, so if this formula represents something that's going to converge, what do we know about r? It's less than 1, or?
Well, it's in between -1.
It's in between -1 and 1. So if you take a number that's between -1 and 1 and raise it to a huge power, what happens? Like, say, take a number between -1 and 1 and raise it to the 900th power. It's a really, really small number. In fact, what does it approach? It approaches 0. So as n starts to get really, really huge, like a billion, if you take a number that's between -1 and 1, 0.4, raise it to the billionth power, it's basically going to be 0. It's going to be extremely small. So we can ignore it. We don't even need this part. So all we're left with is a sub 1 times 1. We could put that in the top, over 1 minus r. So that formula that I just wrote on the right-hand side tells you the sum of an infinite geometric sequence, which I thought I had somewhere. Oh, I have it right there. So that's the formula. That's what it would converge to. Now, this formula has no meaning if r is greater than 1 or less than -1. It means nothing. You can plug r in, like let's say r was 2. You can plug it in, but the answer that you get means nothing. Okay? This formula only has meaning when this condition is true. Okay, so any questions on why this minus r to the n just disappears? Why it just gets so small, it just disappears? All right, so let's use the formula we just came up with, a sub 1 over 1 minus r, to find the sum of an infinite geometric sequence. Okay. So those are the two things we need to identify. What's a sub 1 here? 5. And what's the common ratio? Half. So before I even plug it in, I'm going to ask myself, does this converge? Yes, it does converge. And how do we know? Yeah, it's less than 1 and greater than -1. It's between -1 and 1. So now we can use the formula, and the answer that we get is going to be the sum. All right, so how would I write out my formula? What goes on top? 5 over 1 minus a half, which is a half. And what's 5 divided by a half? 10. So if you were to add up every number in this sequence from 1 to infinity, it would add up to 10. So you would say the sequence converges to 10. The individual terms are converging to what? 0. They're getting so small they don't even make a difference. But the sum of the terms is converging to 10. Yep. Okay. Any questions on that? Did anybody have any other questions in general on sequences or series? Because that pretty much wraps up series for today. Okay, so tomorrow we'll finish up what we're going to do in Chapter 11, which is the binomial theorem, 11.3. We have our last test for the year on Friday. Okay, it's just going to cover what we did this week. Make sure if you still owe me a test from last Friday because it was a field trip or something and you were out, make sure you come see me and get that done by Friday. Okay. All right, so homework is on same page as last night, 601. And it's 21, 22, 29, 30, 32. And the rest is all. So 33 to 35, 37 to 39, and 42 to 45. Okay, and you've got quite a bit of time. You've got about 20 minutes to start that. So I'll unlock the graphing calculators. There's some extra books on the back counter. Okay, if you want to start that, and if you finish it, just show it to me. And there's no other homework tonight.